We're all just waiting, right?
Yeah,
Okay,
uh,
cool.
I'm actually ready, so whenever the chairs want, I can get started.
Okay, I just want to make sure my audio wasn't broken or anything.
Did anyone else receive a odd cancellation notice for the wrong time this morning?
Yes.
Yes, 10 a.m. Yes. Yeah, it might be for this then.
It wasn't from Brian or Jeff, though,
Correct.
True.
but neither of them seem to be here either.
Yeah, it was from Bruno Mussard, whom I don't know.
So I have an email from Jeff. He was saying that he won't be able to attend, but uh, Brian actually should be, unless there is a time zone confusion.
If not, I think we could just continue. Let's start. Anyways, it is being recorded, right? So yeah, they could join later. Let's
Sure,
just use the time.
yeah, sure, that's fine for me. So I would still need some help from someone to kind of monitor the hands or the chat because I have just one screen. I'm going to share this screen. Okay, so get rid of this. Do you see the slides?
Yes, we can see your screen.
Okay, perfect. Yeah, thanks for having me. I talked about a couple of OCP talks in the regional summits, and we have made some progress on this. And as I mentioned in the um, list, we have now a new working group in the IETF, namely SEAT, which is going to work with the TLS protocols. And the aim here is to get some feedback from this community about what could be the possible the kind of goals, because the scope of SEAT is wider than confidential computing that I have been very much focusing on. And the idea was to see if there is any feedback on the work we have or any other goals that might be relevant, for instance, for non-confidential computing use cases that we might need to consider in the design. So that's the main objective. And as always, I want to thank all the people that are listed here who have been actively contributing to all of the work that I'm going to present. So my idea is to talk about the model and the approach that we have taken. Parts of that was in the preprint that I shared, but I will just high level go through it to kind of show what we have and the vulnerabilities we have discovered and the solution that we are trying to standardize in the ITF, or the one that we have proposed out of all the outcomes of the discussions. So this is a bit of a overloaded picture, but the aim was to put together all the things that the system model contains. Often it's a bit unclear what we are talking about, and there are a lot of keys, as you see. Let's start from the left side, which is to say, and please feel free to interrupt in between. It's meant to be more of a discussion rather than me just presenting. So kind of, I would like to have discussion in between if you want, or if something is not clear. Starting from this side, from TLS perspective, this is the client playing the role of the client. And from RAT's perspective, that's acting as the verifying relying party, meaning that the verifier and the relying party are co-located as per RFC 9334. It has in its trust store or trust anchor store the two public keys corresponding to two different machines, which are physical machine 1 and physical machine 2 with attestation key 1 and 2. Question? Okay.
I
Then,
think the question was, you said contains the public keys, but I think you meant private keys. Is that correct? Because you were pointing at those.
So public keys corresponding to the private keys. So
Okay.
trust anchor store will contain the public keys corresponding to these
Got
private
it.
keys.
Okay,
Right.
thank you.
Because otherwise, if this has the private key, then that would be problematic. Only this key should have this private key. And now the left side hopefully is clear. So let's move to the right one. So this is one physical machine. This is just a replica of that, just to show that the infrastructure has multiple of those machines. So the left side of this is basically a copy of what is here. So I will only explain one. Infrastructure provider, just a generic term. Terms are a bit confusing. This means it could be a cloud provider. This is more generic than a simple cloud provider, in order to take into account not just the public cloud providers, but also, let's say, other scenarios like WhatsApp, meta servers, and data center. And so let's start now with the physical machine, which is identified by an identity IDS1. And within that, some parts are untrusted, which are here, and some parts are trusted, which are shown via this attester 1, which will be actually attested or measured. And that would contain, for example, let's start from here, then I will come back to this part. The CC platform, from ARM perspective, that will mean that it's the platform attester. And from Intel SGX TDX perspective, it will mean that it's the PC provisioning certification enclave and the hardware and the firmware below that. And this, from TDX perspective, will mean the quoting enclave, generically represented as quoting agent with the attestation key, which is doing the signature. From ARM CCA perspective, it will be the RMM. And on top of that, we have the VM virtual machine. And each of those virtual machines is identified by a specific key. I call it EK. That's not endorsement key. That's the ephemeral key to distinguish it from a long-term key, which I will then define. Meaning that it could be short-term. It doesn't have strictly ephemeral sense, but that's just the name that was conventionally used. EK referring here that it's the identity of this specific VM versus other VMs and versus this whole physical machine. So a virtual machine is identified by this key, and a physical machine is identified by this specific key. And the idea is, or the requirement is, that I could have a consensus protocol where I could have valid replicas with exactly the valid.
Yes, can I interrupt one question? So when
Sure,
you
sure,
stop,
please.
you're basically showing a sequence of keys, right? Starting with physical machine, then secure
Right.
element, and then quoting agent and the virtual machines,
Mhm.
right? So
Exactly.
are you assuming to be kind of a dice chain here?
Not necessarily, but
So
this
where
is just yeah.
okay, because I'm trying to understand whether these keys are related or how these keys are being generated. Or if it is a part of dice, I can understand that you start dice chain from the physical machine, and then you extend this this dice identity to all the virtual machines, right?
So what I'm seeing here is that this is more generic than DICE. Doesn't need to be DICE. Just I
Okay.
feel
Yeah.
what I'm seeing here is that there is a CPC platform that could be the target environment. So what
Okay.
are the basically what is in the TCP or the gas VM from the platform side and designed by the quoting agent? The quoting agent private key perhaps can be a DICE key, but that depends on the platform implementation.
Okay.
And but now we just saying there is a quoting agent here, and then there is these VM keys which are ephemeral because they say they can change when the gas VM. So perhaps are related to the lifetime of the VM or something like that.
Okay. Okay.
Right.
Thank you.
Exactly. Yeah,
Thank you.
that was a good explanation. So DICE is one implementation, but not necessarily the only one. Can be in different ways. And the relation I will also explain about these keys. The relation is best explained by this one. So that's an evidence which is containing the public part corresponding to this private key, that is the pub EK, and the state meaning containing all the measurements of this attester, meaning that it has the and all other claims in general, also including the nonce and all that, whatever is required there or whatever is used in the protocol. So it's per VM. That will be for, let's say, for this specific VM plus this quoting agent plus CC platform, and the relationship of this key and this evidence will be signed using this attestation key. So that's the relationship between these two keys. That
Yeah,
is,
but when someone is verifying, so it's
Mhm.
the verifier supposed to, so there will be independent certificates for each thing like VM, quoting agent, and the secured element and physical machine. When the TLS client is verifying, right? When the attestation response comes, so is it supposed to verify
Right.
all the certificates, right?
Right. It's from the evidence perspective, it will have the public key corresponding to that private key in its trust anchor store.
Yeah.
And with that, it can verify this specific evidence. And
Yeah.
together with that, it will have also the which is not shown here in the figure, like which will be this key, this certificate will be signed by the CA. It will similarly have in its trust anchor store the public key of the certification authority with which it will verify this specific certificate, which is for the physical machine versus the virtual machine.
But
Yeah.
Does that
why would you
clarify?
have both of those in your trust anchor store? Presumably,
Exactly.
the
So,
long-term key is endorsing the AK.
so that's something that I will formally explain later on. I will keep this question pending. If it's not answered, please let me know then, because it's a bit complicated. That's related to formal analysis, how we, or the text that I will show in section number 2.
So one other thing is that kind of like confusing here, like when you say pub key in the evidence, kind of like look like it is an endorsement key, but it's not an endorsement key at this point because this is the key. Like, so basically the assumption here is the evidence is provided as a sort of certificate, while the evidence can be technically a hit, and the hit doesn't include a key in the, like, doesn't have any key associated to that. Like you are talking about an identity attestation the moment you have a key associated with the evidence. But the
Okay.
evidence can be also not, like, can be an inventory attestation, like for example, like a hit, and the hit doesn't have to include a key associated with the evidence itself.
Sure. So I'm trying to, okay, so this, I completely agree. This is very focused on confidential computing, where, as I was mentioning before, that the virtual machine, I might have a consensus protocol where while the other virtual machines might have the right measurements, but I do not want them to disturb my consensus or put a wrong majority or write concurrently to different files. So that's why I want to distinguish each instance of a virtual machine, even if they are valid, they should be checked that which identity is the one which is writing to a specific file or contributing to the consensus protocol or majority protocol and so on. So there is a value which is required. Plus, in confidential computing, we do not trust, or we do not want to trust the this infrastructure provider, which is, or that's what Confidential Computing Consortium claims. So the idea is that it cannot be involved in the certificate issuance. That's why it's a self-generated key within this virtual machine in order to get the communicate with that with the TLS client, so that this is not in the TCP. That's the purpose of this specific key.
But is that
But I agree
rooted
that
at
this
all?
is
No, when you
but-
say self-generated private key, is that
Right.
rooted at all from the image owner, as in the image manufacturer, like the virtual machine image when it was created? Was that rooted at all, or is it completely ephemeral and only created at the time when the instantiation of the virtual machine happened, and then it will go away the moment it is killed?
It's the latter of the two that you mentioned, because if you already give it over as part of the image, then the infrastructure provider has that image, right, in the plain text. And it has to be generated on the fly at the time it was running so that it's not available to the infrastructure provider. That's the idea. Does that
Okay.
answer your question?
Yeah, got it, got it.
Okay.
So that's why you're saying, so, okay, I mean, again, I'm kind of logically putting together,
Yeah.
looks like that's the reason you're saying in your trust anchor, you don't have the corresponding public key evidence because they're not pre-generated at all, right? You only
You mean for
you
this
can
key? You
probably
mean-
have the public keys for the platform. Is that not possible at all? Or why are you not having the LTK1 in your trust store?
So that was, as I explained in the other question that I think Matt was asking, that I'm not explicitly showing here, but there is a LTK actually is not required to be in the trust store. It will be the certification authority which is required to be in the trust store. I mean, that's the PKI, right? So what the CA will do, it will sign its identity, let's say azure.microsoft.com, with its public key by the CA's private key. And if I have that public key corresponding to that CA's private key, I can verify that this certificate is correct.
Okay, got it.
Right. Any other question, or should I proceed? Okay, hopefully that's clear now. So with that, I have a set of informal security goals before going to formalization, just to discuss. Of course, I do not discuss formalization here. That is basically for remote attestation. So I have two things in attested TLS. I want to first, coming back to it, sorry. I want to establish a secure channel to this trusted execution environment, and I want to have it attested. So there are two separate things which I have that from TLS and from attestation, and each one of them have their own goals, their own threat model, and we want to preserve both properties. That is to say, informal security goals for remote attestation, then there will be for TLS, and then there will be for composition. This is how we view of all of this. And for remote attestation, of course, I want evidence not to be modified, evidence to be freshly generated. What does that mean? That means basically that there is a binding between evidence and a specific remote attestation interaction which has happened. And also, in addition to that binding, it has to provide some recentness of the evidence generation, that it is recently generated. It's not an old one. The third property is establishment of connection with attestation key known to the adversary, which means that if there is an adversary in between this communication and I have this attestation key, meaning this private attestation key known to it, of course, it can change everything and mess out with the whole protocol. Similarly, establishment of connection with ephemeral key known to the adversary. As I said, EK is representing ephemeral and not endorsement key. And if this is known to the adversary, of course, it can impersonate this specific virtual machine. So these are the four properties that we have verified, and or let's say informal security goals, converted it to formalization and verified those. And then for TLS, there are standard TLS properties which have already been formally verified and analyzed and standardized. RFC 8446, Appendix F, I think F.1 or something like that. To summarize them, that's basically similar to this one: establishment of a connection with client's write key. Write key here means the one with which client will encrypt its secrets or its confidential data, or for provisioning, after which it will provide the key to decrypt this image that it has sent out to the infrastructure provider for running that. So that key, of course, is very important, because if somebody else gets that and establishes a connection with a client and pretends to be that, that's really bad. Secondly, server authentication, that there should be no man in the middle in between the client and the server. Finally, the composition of the two, meaning composition of remote attestation and TLS. Now we have separate properties, but what we want is that the evidence, the server that actually generated this evidence or the one which was authenticated is also the same that is generating that evidence. And it's not that I'm connecting to someone else, but the evidence is generated by someone else. I will show in one of the attacks later on. And the way we put it is as binding evidence to a specific TLS connection. If it is evidence is bound and unusable in other TLS connections, it's one way of providing this high-level composition goal, which from a technical perspective, if some of you are deep into TLS protocol, can be achieved at 3 different levels. There is GXY, that is the shared key, which is established in first part of the TLS protocol, which is key establishment phase. GX, GY, and both can then compute GXY, the shared Diffie-Hellman secret. And then there are 2 different secrets, which are in TLS handshake transcript secret for client, because the client is the one which is encrypting that secret data. We have to protect that from that perspective. That's the secret with which the handshake traffic is encrypted. So it's including more information than GXY. So it's the second level, so to say. And the third level in TLS key hierarchy is the application traffic secret for the client, with which it will actually secure the secrets that it will send over to that confidential VM. So, and in the key schedule, they are hierarchical. That is meaning that they are basically including more and more of the key of the handshake transcript. And that's why the level 1, level 2, and level 3. And finally, that
Like, can you define the
yes, sure.
what is the definition evidence here? Evidence is the identity of the virtual machine, or then you're saying binding it to the underlying connection also, because when you see a GXGY, basically the TLS connection and the session, right? And then your and session has some shared secret, right? You're trying to bind it to that, the identity of the virtual machine to the underlying connection, right? Is that what you're trying to say? I was a
So
little bit lost actually.
sure, I can try to explain. By evidence, the first question you asked, by evidence I mean all the claims. ST is representing the state of the that virtual machine, and plus all the components underneath.
So can you
From
explain a little bit more, elaborate on that? Virtual
sure,
machine is the end entity, and that is talking over a specific connection, TLS connection, basically binding that
right.
identity to the connection. That is what you're saying?
So that let me put it like this. So network stack is here. The connection, this connection
Yeah.
will terminate within this virtual machine.
Yeah.
Because we cannot terminate it here, because otherwise then
Yeah.
other virtual machines also see it. We cannot also terminate within the physical machine because the infrastructure providers see that, right?
So
Okay.
they can a lot of parallel sessions going from this client to VM1, VM11, VM12, VM12,
Yeah,
13, and so on, right? So there's several parallel connections out there. So they're trying to
right.
connect this virtual machine to the specific TLS connection, right?
Right. So we are saying that we put some key material from the TLS connection.
Yeah.
And not necessarily the key material. Let's put it more generically, like something from the TLS connection into that evidence is what I mean by binding.
So basically what you are doing, you are basically with the classic TL connection, you have a static binding based on the certificate key that you have in your trust store. So you basically have an identity authentication only. What you want to do, you want to basically do TLS, binding TLS with attestation, basically putting an evidence inside the TLS mechanism to establish trust into the device before starting the secure session.
Yeah,
I think it's the other way around, the one you mentioned. It's not something from the okay, so of course, like the evidence may be a part of. So let me just clarify maybe one thing. So then of course I will come back to you. So the thing is that there is a difference between binding versus conveyance. So if, of course, I will convey this evidence within or after this TLS connection, but that's not binding in a sense. Like it's just saying, it's just conveyance.
Yeah.
When I say binding, that means actually I have some something from the TLS connection put into my evidence, which makes this unusable for any other connection, any other TLS connection. That's what I actually meant.
Yeah, so that is what I think there are the two phases, right? One is the handshake phase, and
Mhm.
other is the where actually you start you generate a shared secret and you start with the right key, what were you saying, right? Using that, you basically start sending encrypted and authenticated payload, right? So
It
basically,
depends.
yeah,
Basically, it depends. That's not
yeah.
fully correct. That's true for post handshake, where you will have evidence after the TLS connection is done, but you could have it within the TLS connection where your statement is not true. That will not be, then this one will be generated within the TLS connection. And by the time TLS finishes, you have the evidence and everything is done by then. So there are three different ways, pre, intra, and post. It can be done in different ways, but the idea is so these goals are meant to be more generic. Like this is the requirements that we want to have a secure protocol. It's not specific to, let's say, pre, intra, or post, or how you do it is your innovation. We tried two different solutions from industry, what we verified. And what I'm saying here is security goals, meaning that for a secure solution, these goals should be satisfied.
So basically, this is what I see the advantage of this one is that basically the client who want to connect to the server, want to establish a
Yeah.
TLS connection to the server, will know priori to establish the connection what's the TCP of the entity who is establishing the connection with. So through the conveyance of the evidence which is bound to the TLS key. So basically establish authentication of the TLS key, make sure the TLS key is trusted, then use the TLS key to authenticate the evidence, and will basically do an appraisal policy of the evidence, and also after success of this appraisal policy will establish the secure session with the device, with the VM, right? Instead, what is done right now is without this proposal, you're first establish the connection, and then there is conveyance of the evidence, which is not bound to the TLS key.
So what you're saying is one specific proposal. I would say the one you mentioned before. Again, what I'm saying here is the goals are independent of a specific solution. I will show two specific solutions like Intel's RATLS, which is very common. And there was a previous internet proposal of intra handshake. So these goals, I think of them as completely independent of how you actually do that. Whatever protocol you design is the how part, and this is what I need. So this is what I want to have a secure protocol. Whichever protocol you design should actually satisfy these goals.
Yeah.
So
we are saying the same thing here, yeah, because you have the composition goals basically that doesn't exist right now.
Yeah, okay. If you talk about there are some attested TLS protocols already in industry, like confidential computing doesn't work without attested TLS. So I wouldn't say they don't exist. I mean, the goals are what should be satisfied. Protocols exist, and a lot of research has already been done. But the question is whether these protocols satisfy these goals or not. This is how I will, or at least I view it.
Okay.
Does that clarify that?
Yeah, no, yeah, that clarify, yeah, like,
Okay.
yeah.
Okay, very good.
So basically, the way I'm understanding is that there's a TLS connection where you basically you verify a certificate, but the certificate, you're not just verifying certificate, you're also attesting the identity, right?
At a high level, yes, I would say we want to have both. Like we want to have a secure channel. We also want to have that via PKI, which is this one, and then attestation of the state of that specific one.
Yeah, I got it now. Yeah.
Okay, very good. Then I will proceed or quickly show just the approach, high-level idea. There are, as I said, so security goals, as I showed, are what we want to achieve. Protocol is what one can design in order to achieve these security goals. And there is a lot of innovation that can go here, like pre, intra, and post. Multiple solutions exist. Multiple academic proposals also exist. It's a bit hard for engineers to kind of get their head around these kind of things. So what we provided was kind of explanations and visualizations for the logical formulas. And I will not go into the details of this. And for this, what we want is also on this formal side, we provide some explanations. So whichever level, let's say a designer is, can get into these kind of things. And the main idea we have is that mathematicians do very high level verification typically, and that doesn't include many of the architectural details. On the other hand, designers cannot understand what all these mathematics mean. So what we propose is protocol designer in the loop that both work together and have a bit of understanding of each other, so that the verification is also useful for designers to get some insights out of that. And if there is an attack, we provide a visualization for that, let's say, to understand at the protocol level what's going on. That's the high level bit. There are some terms which I will skip for the time. And to visualize it at very high level, so this is the client which was in the previous figure shown as a laptop. This was a server, the big data center which was shown. And to visualize that, there is adversary in between, the network adversary, typical network adversary. And in addition, what it includes is, to the network adversary, also some parts of the server itself, like the physical machine, which I had shown, like this block. For example, the hypervisor and so on are believed to be untrusted, which are not a part of the tester. They are not measured. They are believed to be untrusted. So that's the part which is captured together, not only now the network adversary, but there is also on the endpoint, there are some portions which are untrusted. And from a simplification perspective, I have put them together as one adversary, which is that through via this, it will then connect to this. Every message it can modify. For example, it gets a client hello, modifies that. It gets server hello, modifies that, and so on. That's the kind of depiction of what's going on. Okay, I will pause for a minute here to see if there are any questions. Otherwise, I then show what are the problems that we found or the vulnerabilities in the protocols that exist already. Okay, seems it's clear. So then I will proceed. The first one is a replay attack. So interoperable, as I said, so there are now we are going into this part, which is the protocol part, right? So I showed you some security goals, and now one of the protocols that we analyze is this interoperable RATLS. And from the formal analysis, now I'm going to show you what attacks were there and how do we kind of show that visually, that from this trace, which might not be understandable for an engineer, that what does it mean to have this kind of a trace. But this visual, probably most of you can understand that there is a server here, there is a client here, moving or visually seeing back to the first figure that I showed. And what is going on here is basically that a client, a malicious server was able to convince a client into accepting two different connections, the connection one here, which is going on here, and then another connection in which the same evidence was replayed, because interoperable RATLS does not have any freshness check. That evidence is does not contain any freshness criteria, any nonce and so on. And hopefully then this is of course abbreviating it to make it more simpler to read, like 1A and 1B and so on. They represent these messages. But we believe that this is how a protocol designer can get more insights into, rather than saying, hey, there is a replay attack. This visual will help it get to the core of the problem, that what happened in the attack trace and how to fix that actually. So in a nutshell, like there is, from a trace perspective, for server is finished, like server finished just once and client finished 2 times. That's the high level view to visualize it. For the second one, that's the internet draft. Again, going back to the picture, that's the second separate protocol, which does have freshness. So it doesn't have the problem of replay attacks, but it does have another problem, which is that diversion attack. And that's what I will show you now. What it does, and hopefully it will answer also Matt's question, that why do I need 2 certificates, or why do I need PKI in addition to evidence? And Matt, please let me know at the end of the next slide if it doesn't answer your question. So a client wanted to connect to cloud.example.com, which was running in this TE. And what happens here, it provides this evidence which has these measurements and all the claims and the public key. But what an adversary can do is to reroute it to another data center, which is completely different one. Let's say it was a Meta data center and I was communicating via WhatsApp over to you with some private data. And what it can do is it can reroute it from this one to anything else, like maybe a server in my basement, because it never does the proposed protocol, this TLS attestation draft, internet draft, which was proposed in the TLS working group, never checks identity at all. It just checks that it has the correct measurements and the claims, and that's it. It doesn't check anything that it's connecting to the right server, which I expected, like the cloud.example.com, or let's say whatsapp.meta.com and so on. And it could be rerouted over via Dolevia adversary, the cloud that I had in between the network adversary, to any machine. And if for that specific machine, we have the attestation key that that one has, let's say, by some means extracted out. And there are a number of ways to do that, because the confidential computing threat model does not cover actually that you have a physical access to that specific machine. So you can actually do these kind of attacks. And then with that key, you can reroute other connections over to your machine for that key which you have extracted. And it has actually practically been demonstrated, like wiretap and this other attack have actually demonstrated that this is also possible. Like we showed this to CCC well before in February and so on, I think, when we did this analysis, but it is actually exploited and practically demonstrated that this is possible. And what we call is the identity crisis, meaning we don't actually, I have a slide next which shows the kind of solution to have both, but Matt, does it answer your question?
Yes, although I'm not sure you had the right key in the, like, if we go back to that slide, I may take issue with which keys you painted in the trust store, but I get the problem. Like, I get this, right? You need a binding both to the domain name and to the attester. So,
sure.
like, you need to, I get you need 2, so that's fine. I don't know that the AK is the one you need here. I think it's the actual, I think it's the long-term key that you need there.
You mean, are you talking about this trust store?
Yes.
So AK will be required to verify this evidence. You cannot verify unless you have this AK in your public part corresponding to this private key. You can never verify what that evidence is. And
the AK would, so depending on how you're doing this, right, when you, and maybe this is because you're using AK and I'm thinking of TPM AIK, but normally, like, your attestation key would be endorsed by the long-term key.
Yeah.
So
That's
you don't need the pin to the AK. You need the CA for the long-term key is what you pin to in your trust store, and the AK would be endorsed by the long-term key. And then your EK needs to be endorsed both by the AK and by the other thing that proves domain ownership.
Just to be clear, so this picture, and as I said, the whole as the title, so this is about confidential computing. There, for example, in let's say for ARM CCA, this will be the realm
That's the
RMM.
Yes.
Yeah,
That's
so
the
that's the
rack, but you
RMM.
you
That's
never pin to the rack on the client side. You must not, because the rack is ephemeral itself.
So
Rack is not persistent long.
that's. But with what view will you verify this evidence? This is the key with.
you
Okay, so
can
let
have an
me.
endorsement
Rack is
key that is on
The rack
top
is
of.
endorsed by the platform
Yeah.
certificate that is signed by the device identity, which is your long-term key
You-
here.
You cannot pin that attestation key. The attestation key, like in one specific example, like we say that this is more generic, but attestation key can be like your dice key, like which is changing with when the firmware changes. So you need to establish trust into the attestation key. So you need an endorsement key, which is a long-term key, like an identity key, which endorses attestation key, and you can endorse that one.
Yeah.
So is there some material that I can read? Of course, as I said, so I am more familiar with, maybe let me just address this comment. For instance, let's say the one I'm more familiar with, of course, CCA is under development and it can go some changes. But for instance, like for Intel SGX or Intel TDX, that's the attestation key with which you will, and that's the quoting enclave with which you will sign these evidences.
Yeah, the
And
basic.
then there is a whole chain, which is the attestation key, PCK, and then the Intel's root trust, Intel's root key. So you could have
Yeah.
that public part corresponding to the root, Intel's root key. Then you need more certificates like corresponding to
but-
that.
No,
Yeah,
but
yeah, you're getting the right
PCK is the
thing.
long-term
Basically, you need
device
the
key, right?
you need the
So
whole
this
root
is
chain, basically chain of the
sure.
certificate.
So
But
this
the
is,
long-term
yeah,
key, the top one is the long-term key. That is that you have to verify the whole chain, right? And chain to the
which
long-term.
one, which one are you talking about? I'm a bit confused.
No,
Are you talking about this
so the quoting agent also has certificate. Who is signing that certificate?
PCK? So that will be signed by PCE. So
PC.
so there is a whole certificate chain which we
And
have in a very
that
separate separate paper, which is to say you have a VM,
yeah.
and then you have a quoting agent, then you have provisioning certification enclave,
Yeah,
then you have the Intel's root key, and each of them have a certificate corresponding to that. I have a nice figure for that.
So that is the
So
long-term key. That
yeah,
is what the last one that you said. That's the long-term key. So this is a whole chain, right?
the
So
the root
Yeah.
Intel's root key, you mean? Oh yes, sure. That's
Yeah,
that's like
yeah.
7 years or so on. So I
Yeah,
think, and
yeah.
even 15 years. I'm sorry. Like
yeah.
I think up to the quoting enclave and PCE, they are 7 years, and the one for the Intel's root key, that's 15 years.
Okay,
So typical lifetime.
The quoting enclave key, is there a guarantee that that's persistent? Like between sessions? If I reboot the physical machine one there, am I guaranteed
Yeah.
to get the same quoting enclave key the next time it boots up?
I have to look back into it. So I remember that is there were some factors on which it was dependent. One of them was BIOS. You can change some parameters there to have a new key. So this is dependent on some of the factors. So if you change those factors, you will have a different key. So I think if I remember correctly, you can change it, but not necessarily by a reboot. That may not be that can be the same. That's what I remember. But I have to see what factors that is derived
Right.
from.
If you want to store it in the client trust store, like you need a guarantee that it's persistent. And I didn't even think the QE key was. And I know for ARM CCA, the rack is not, you have no guarantee that the rack is persistent.
Okay, sure. I will have a look. So
if you
just
look at
to
the ARM spec, the platform token endorses the rack. And so you know the rack is valid because you've inspected the platform token signed by the long-term.
Sure.
But that's the only information you get about the rack.
Sure, that may be fine. I have to recall we did some formal analysis like 3 years ago for ARM CCA. I will have to check that, but I would say from formal perspective, it's a kind of an abstraction that I have done rather than going to, as I said, what I remember more is the Intel's chain, which of course goes back to the Intel's root entity. And this is a kind of a simplification that I'm saying that instead of going to that complexity from virtual machine key, then quoting agent key, then provisioning certification enclave key, then Intel's root key, I'm just simplifying that. I have this key, I do signature with this, I verify signature with this, which is equivalent to, not equivalent, I would say maybe analogous to doing that at some abstraction level that I check rather than that. In that paper, we did actually the whole chain, that the one that I'm mentioning.
I mean, as far as your protocol analysis goes,
Yeah.
it's probably true that if you analyze that, like
Yeah.
because pub AK you will always have, or you better have like a valid endorsement chain back to some root CA that you trust.
Sure.
So if,
Yeah.
if you're just cutting off that part of the analysis, fine, but it's just weird to see the AK in the trust store.
Mhm. Yeah, sure. That will complicate the picture a bit to put the Intel's root key, but
No,
I will take this. Yeah.
So here is my concern, Osama, is
Yeah.
that like we are saying at the beginning, we made say that we don't want to make assumption about how the certificate chain is formed, whether you use dice or you use dice. But then at the same time, we are making some assumption about Intel TDX here, for example. Like I
No,
think
no.
we need like
There is no assumption here on Intel TDX at all. The verification is completely independent. The one I was mentioning was
no,
3 years ago.
about the Intel TDX, so now it use like this AK. Like I think we wanna like what it will help here is to build a generic certificate and key hierarchies between this AK, between EK, the LTK. How would you expect there is a hierarchy between those keys? At least grounding the assumption in those hierarchy of keys. Otherwise, like people like me or probably Matt or Sanjay, like looking at here, like I really don't know by just looking at the picture how those keys are related one to the other. And then you're mentioning Intel TDX or ARM CCA, which I'm not familiar with neither of those. So I don't know how those
Okay.
work.
Right. Yeah, sorry for that. So I will,
Yeah.
first, just to clarify, so it's completely, the verification here is completely generic. It's
Yeah.
independent of TDX.
Yeah, so basically
And
it could be TDS, it could be AMD,
yeah,
SCV, SNP, or it could be ARM, CCA, right? So it could be anything.
exactly.
So they have the same. Everyone has the same, more or less same concept where
Yeah,
a guest can run. They can the notion of guest virtual machine by different tenants of the cloud, right? That can also.
exactly. Like, I mean, I provided you one analogy that confidential VM is, of course, like it true in all confidential VMs,
Yeah.
technologies, TEs.
Yeah.
And this quoting agent for Intel SGX and TDX will be quoting enclave.
Yeah.
And and then provisioning, this CC platform will be provisioning certification enclave and the hardware firmware underneath. And for CCA, this will be RMM. This will be the platform attester.
Yeah.
So
Uh,
it has analogy with each of those. I mean, the verification is completely generic. I have not made any assumption
Yeah.
whatsoever for Intel TDX. We got that kind of insights in the work we did before, but from that we have now abstracted away, and this is completely generic. But what I acknowledge is that it's missing the relationship between the keys, which I will add. I completely agree with you. Maybe it's confusing a little bit. I will make a small chain. That was an abstraction that I did to kind of avoid all that chain, but it might be confusing for people. So I will add something somewhere to show the relationship between the keys.
Yeah, that
Thanks.
would be very helpful. Yes. Yeah, because I think most of the
And
discussion with me, myself, Matt, Sanjay, were kind of like related that we like don't know what was this relationship and why. Like Matt asked the first question, why you put the AK in the trust store? Like if you knew like how the whole hierarchy of keys will look like, we will have understood why.
sure. And I would love to have some contribution from the experts here on DICE and TPM because I'm not an expert there. I have looked very deep into Intel TDX, SGX, and ARM CCA, but not yet very much into TPM and DICE. So if somebody is interested, I would love to have some contribution there so we can generalize even more to have these, to see how these hierarchies fit together and that would be very interesting. That would be very interesting contribution. Okay, so looking at the time, I'm going to quickly just show you the rest of the things that I have. The third attack is the relay attack, which is a bit simpler and already known in the industry. That's not an innovation. So this diversion attack was something that we found, which was not known before. But this relay is simpler and is known. That is to say, I have a verifying client party, meaning the client. I have adversary in between, just like the figure I had before, and the genuine attester. The adversary gets the nonce, forwards it to the genuine attester, gets that evidence, and presents as its own. If there is no binding between the two protocols, remote attestation and TLS, so this can happen. Or even if there is a binding, but a weak binding, then this can happen that the evidence will be accepted at verifying client party, and it will establish an attested channel thinking that it is communicating with this genuine attester, but actually it is the connection is being terminated at the adversary side. So with that, I will quickly show you one solution or the high-level solution, which is very simple, that I have PKI, I have this certification authority, which is kind of showing the standard PKI. I, for example, provide the public part of the corresponding to this key of the certification authority over to the client. And the server has a key for which it sends over CSR, gets a certificate, and then it runs TLS connection with that, providing it a certificate in that connection, standard PKI TLS. And on this side, the picture for the remote attestation, which is hardware manufacturer, is the trust anchor, provides or provisions at the manufacturing time, typically this attestation key. This is generated afterwards, the ephemeral key, which I had on top of that figure, and it then interacts with the verifying relying party with the assumption that somehow, and there's a big somehow, how that will happen is still a question mark to me, that how that will be actually provided to the verifying relying party. I make an assumption here that all of this part, number 2, is secure, and somehow it has provided it over to the verifying relying party to check that evidence that it will get at the end of the chain. The key idea of this slide is we have completely different things which this is providing. This is providing identity of which server I'm connecting with. Am I really connecting to Meta for sending over my private messages? And on this side, what is the measurement of that device that I'm connecting to, and the state of that, or in general measurements and so on. Both are complementary and both need to be taken care of. That's the key point of the solution. And that's for diversion attacks, which it can fulfill. And to quickly show you this proposed solution that we are now standardizing in the SEAT working group, or proposing basically, is the post handshake solution, which means run a standard TLS, no changes in this. And afterwards, the one-way authenticated channel is established via TLS handshake. Use RFC 9261, which says authenticator request, which consists of this client certificate request message, provide a attestation nonce in that, and then get back these 3 messages together called as an authenticator according to terminology in RFC 9261, which contains in this certificate the evidence which I showed you back in the first figure. So the first certificate is in this part, and the second one, which is for the evidence, will be in the post handshake part. And by checking both, it can ensure that it is connecting to Meta and it's also having the right measurements that it expected. So
Can I,
with that,
is the,
sure,
is the evidence, when you say certificate, can be a certificate chains with basically signs I hit and basically being the evidence I hit? I don't know how those API are formed, or is there any syntax that this can be a single certificate as a response from the authenticator?
I couldn't follow your question. So are you saying that whether it's...
Can you put basically it here, or it must be a certificate?
It doesn't necessarily have to be a certificate. That's
Okay.
So what we are doing, actually proposing, is to put in CMW, even the conceptual message wrapper, in case you are familiar with that.
Yeah. That makes
Okay,
sense
very
because
good.
we'll include
Yeah,
both the
yeah.
certificate chain and it
Yeah.
in that case. So yeah, that will make sense to me.
Yeah,
Um,
sure,
go
go ahead.
No, I was going to say my only comment here is both on this slide where you're saying the standard handshake using the long-term key, and then on the previous slide, the different private key names, probably need to reconsider some of that, because in general, like your TLS server would not have access to the hardware long-term key. In fact, that's not an in general. It should never have access to the hardware long-term key.
So this is basically a proposed part. So this is not, I should have clarified. So this is our proposed solution, but this part is not formally verified. What we have verified is only this protocol TLS attestation internal draft and the interoperable. So this is still under discussion. Next week, we will be
Okay,
in the
so
IETF discussing.
if you go back to one slide back,
yeah, sure.
That server private long-term key that you're endorsing for like the standard TLS domain name, like that cannot be the hardware long-term key, because it's your VM that is holding that TLS key that you're using. Right. Normally your TLS key lives inside the VM and is exposed to the VM. You can't.
Ah, okay, I see the problem. Sure. So
yeah, but no, I
basically
don't think that that's the problem is, Osama, you didn't explain what the exported authenticator was. I think that's why I had my hand up. The exported authenticator, right, it can't be said separately. It has to be part of the evidence. Otherwise, you'd have no binding of the attestation with the TLS session. So,
but the server on the right must not have access to the hardware long-term key.
yeah, that's fine. I don't disagree with that, but I think that wasn't really what was being depicted on this slide here.
But again, if you go back to the previous one, you would never ever have like your web CA endorse a hardware key like this. That's nonsensical, because your TLS domain resolution isn't tied to hardware secrets.
Yeah, no, I understand that, but I don't believe that I don't believe attested TLS is meant for standard web PKI. I think it's meant for something. Yeah, I think it's meant for something.
That's correct.
Yeah.
So web is explicitly out of scope for us. We have explicitly mentioned that as out of scope. But Matt, just to be clear on this, so this figure is maybe a bit confusing because it's not saying the complete picture. So probably what you are trying to say is that this initial handshake should be with the ephemeral key. Is that what you are trying to say?
The ephemeral key is the only thing your network stack, when the TLS client is reaching out, has access to.
Right. That's what I would correct. So that's the initial handshake would be with this key, and it would be the other way around, that yeah, there is a mismatch in my figures. So that would be that on top of the TLS connection. This is one question also for discussion. As I said, we haven't verified that. And the difficulty is that this key doesn't exist for normal deployments, right? There is only one LTK. And this figure was meant more from generic purpose uses rather than confidential computing. But if I want to map this one, the question is, or the first initial handshake would be with this, and then on top of that, you provide the long-term key certificate. So it has to be both. That's my point. It has to provide both, and it has to verify both.
The long-term key gets used to endorse the attestation key, not the domain key.
What do you mean by endorse? So what do you mean by endorse this key?
So this is what we were talking about before. The long-term key endorses the attestation key.
Okay, so I think this is so here the long-term key doesn't mean that chain that I was explaining. So here the long-term key means that it's a metadata center, or this is identifying that this machine is owned by Meta. I don't want to connect to, or a client might not want to connect to a basement server that I have. It might want to connect to a secure, let's say, metadata center. That was its main intention. And if I want to avoid this kind of thing, that I don't connect to a wrong server, I need to somehow provide it a guarantee that it's connecting to the right one. This identity will contain that infrastructure identity.
So okay, so private EK needs to be endorsed by a CA belonging to the infrastructure provider, proving that that is a member of their infrastructure.
Yeah, so the Meta, for example, in this case, can provide out of band some mechanism to provide this
Yeah,
the long-term stuff public.
I'm concerned about some of the assumptions built in here, especially when you say that you're explicitly excluding WebPKI. I don't think WebPKI is in any way unique here. Like if you can't make this work for WebPKI, I don't think you can make it work at all.
I think there are privacy concerns there for WebPKI, but I don't see it dependent on WebPKI, for instance, or having a strong dependency on WebPKI. Why do you think that
No,
without
I'm
WebPKI?
saying if you cannot make your solution work, if your solution doesn't also work for WebPKI, I don't think it works.
Yeah, but I think I think the way he maybe not on this slide, but if you go back to the previous slide where you described a test of TLS, right? And not the previous slide, the forward slide. Yeah. This one here. Yeah, the standard handshake still can leverage WebPKI. At least I think that's the way.
Yes, this
this
works, but the keying, I think the keying is very confused here.
Okay.
And you have to sort out the keying. And if you sort out the keying, then this should work regardless of whether it's WebPKI or infrastructure or whatever. But like
Yeah, sure.
Long-term
I have
here, like the keying issue is weird because I'm not sure I can't follow how the keying works out to make this slide work.
So if I have priv EK, does that
priv EK helps?
address your
On
concern?
the previous slide, you have to sort out what those keys are.
Yeah, so this slide is a bit meta
okay,
than the other one because, as I said, so this is more precise. What I have in formal is this thing, which is to say EK is for the VM and LTK is for this specific machine. And this is associated with the identity that is metadata center. And this is associated with all the claims that are sent over as part of the evidence.
Yeah, I mean, but as someone, we have the SEAT working group meeting next week,
Yeah.
right?
Yeah.
This has to be discussed. I mean, when you do the initial
Sure.
handshake, WebPKI should still be relevant, right? I mean, as far as the, so you should still be able to do domain authentication,
So
web domain authentication, if this is going to achieve widespread use.
So
I think the problem there or the concern raised there was about privacy. And what we as authors have discussed is to still keep it as out of scope because people can easily complain about it that this is privacy. They will never accept this to work. So if this works for other cases, it might work as well for WebPKI, but we don't want that to be the only use case, or we don't even want to highlight that in our slides at all. I think if it works, otherwise, why do you think that will not work for WebPKI? Is there something specific about WebPKI that if I have a solution like this, I do TLS with this EK, and on top of that, I provide a certificate for this
I
one.
didn't say it couldn't work. I think you just need to find you need to find a story that it is compatible with domain, WebPKI and domain authentication. That's all.
Okay.
So you're saying this long-term key is associated with the physical machine, but you have it in the attester box, which I think is maybe part of my confusion here. Right? If the LTK is associated with the physical machine, it needs to be outside of that attester one box, right? Like in confidential computing, the TPM is outside of your TCB.
You could also attest the HSM. There is another internet draft, which is, I think,
you can attest it, but it's outside your CC TCB.
Yes. Okay.
Will
so
never
in
be
that
in your
sense,
TCB.
In that sense, yes. Yeah, you can.
You're using the TPM here to verify the physical machine identity, and you're using AK to verify your CC stack. But this is, I think this is my confusion, is you've put those together here, whereas those are Those are the two separate
Okay.
things. And maybe that's been the confusion I've had about LTK versus AK here.
Okay, so I see your confusion now. If I end this attested block at this point, does
Yeah.
that help? Okay. Okay,
Yeah.
yeah, I will, sorry for that.
And then
I
you're
will
endorsing
fix that.
LTK as your root for physical ownership and AK
Yes,
is your root for the other things. And then
for the claims, exactly. And I will also fix this slide, which is saying that, okay, so we do with the EK, which is with the virtual machine rather than the one below. And on top of that, this certificate can then provide also along with the evidence, it will provide you the long-term key. Or one discussion among the authors was maybe we need 2 rounds of this RFC 9261, which is for one, we get evidence. And in the other one, we get that identity certificate, which was this one. So that, but again, is still
I would
under discussion.
assume at that point, you endorse the EK with both chains.
What did you mean by endorsing EK with
You have
both
two
chains?
cert chains for EK. One to your AK and one to your long-term.
No, the long-term key has nothing to do with EK. There is no relationship between this and this.
But that's what I'm saying. You have to create one here, right?
So okay, that's an interesting one. So
You have two evidence chains to 2 different roots, and you have to verify both of them.
so my thought here was that by verifying okay, so there is a connection between the TLS which terminated here with this. There was some material from the TLS as I showed on the binding that was going like this. So some material from the TLS was going here. But your question is, how is that related at all to this machine? I have to think more. It's providing this identity certificate, but I don't remember exactly how the binding with this one was, or how it would work specifically with this. As I said, I haven't verified this one, and it's still in early stages and proposed for discussion next week. Yeah, I don't have some specific insights to share here.
Okay.
Okay, then quickly I will wrap up some key insights. As we discussed, we need infrastructure identity to prevent diversion attacks. Cryptographic binding between the two is very critical. I'm requesting, or we are requesting also feedback on the shared preprints. Seed working group is now formed. We have the drafts on use cases and the other one on the protocol design, and we welcome feedback on that. And finally, I want to thank all the people who have been actively contributing to it, either as co-authors or as contributors. Thanks a lot. And I'm looking forward to your feedback either on the list or to me or on the IETF seat working group. And you are also very welcome to join the meeting for seat and share your insights and how this protocol work should evolve so that not only the confidential computing, but the DICE and so on you mentioned, they are taken care of. That they are very much in scope. It's not limited to confidential computing. That's a part of the charter, and we would love to have your feedback on that. Any final questions or comments? Okay, if not, then
Thank you.
is there? So, okay.
Good topic.
Thanks
you.
a lot.
Yeah, interesting topic. Okay.
Thank you. Bye.
Thank you.